Hello, hello, hello. Disappointingly, this is not Lin-Manuel Miranda, but just your virtual physical chemistry instructor, Dr. Hopkins, with the next in our series of videos, social distancing PChem videos. And this is our second video on molecules or molecular structure. In our last video, we went over in quite a lot of detail the H2 plus molecule, the simplest possible molecule. And now we're just going to add another electron. And so we're going to look at H2, so hydrogen itself, elemental hydrogen. And so the Hamiltonian for hydrogen is shown on this slide. It's very similar to H2 plus. We have the only difference is we have now two electrons. We have the two protons and the two electrons. Assuming the Born-Oppenheimer approximation, you can see, well, we have now two terms for the kinetic energy of the two electrons. We have the internuclear distance potential energy with the 1 over r. That is going to be constant based on the Born-Oppenheimer approximation. We still have the distance between, and actually there should be two terms for this. There should be an RA and RB for each of the, so this should be expanded to include two additional terms. So there's a term for the distance between the proton A and one electron, and proton A and the second electron, and then the distance between proton B and one electron and proton B and the second electron. And all of those are terms we would need to solve. And then once again, we have this R12, which is the distance between the two electrons. And that's the key to not being able to solve this problem analytically. So once again, since we can't solve the Hamiltonian, we can't get the actual wave functions, we're going to do an approximation to it, and we're going to use the LCAO-MO approach. Okay, and once again, this is the same as H2+, so we have the similar kind of Hamiltonian. We end up with similar solutions. Our expectation values, the energies of the two solutions, are the plus and minus that we got for our H2+. And then our two wave functions, psi plus and psi minus. So psi plus is the linear combination where we're adding them together. That's the bottom probability you see on the side there. And then there's the psi minus, which is subtracting between the two, and that's our top probability that we had from the H2 plus. And once again, we have the similar kinds of potential energy curves for the two states. The big difference between this and H2, these numbers won't be exactly the same because alpha, beta, and SAB, all of those are integrals, and they're going to be different integrals for H2 versus H2 plus. They just look, in this sense, they just look the same as H2 plus, but there'll be a difference in the energies themselves. All right, so we have those solutions that we had from H2 plus. Now, if we look at H2, this may be a much more familiar way you've interacted with molecular orbital theory or molecular orbital theory in terms of MO diagrams. And so you can start, you see we have the two 1s orbitals originally on the atoms, then we make a linear combination. So this is one way to represent it without doing the additional math and showing the normalization factor and all that. And so we generate the psi plus, which is the plus. That's like a bonding orbital. And we're going to label that in this homonuclear diatomic sense, the 1s sigma g. So remember, that's a Gerada. It doesn't change sign upon inverting the coordinates. And then we have the psi minus, which we're going to call 1s sigma star u, and that's an anti-bonding orbital. Remember, that's the one that did not have any orbital overlap, or any electron density, probability of having electron density between the two atoms. Okay, and then we'll introduce a new term which you may or may not remember, which is bond order. So it's 1/2 times the number of electrons in bonding minus the number of electrons in anti-bonding. So if we look, and I've placed the two electrons for H2 because we start with two original electrons. We have two electrons there. We put them in both a bonding. That's 2 divided by 1/2. It's 1. This is an indication of bond strength. So the larger the bond order, the stronger the bond it is. if we relate this back to, say, like Lewis theory, a bond order of 1 is similar to drawing one line, or a single bond, if you will. And then the last point from these diagrams, so then we have 2 electrons occupying that state. We have an energy of that state. The binding energy is that energy, and here I have not included the expectation values, but this is the energy of the plus state minus alpha, minus our Coulomb integrals. And remember, our Coulomb integrals were the ionic contribution. So they were the Hamiltonian of 1SA 1 over 1SA, right? Or the Hamiltonian of 1SB, 1SB. So that's how much the atoms want the electrons to themselves. And so that would be the comparison. So if you wanted to put the energy of the alpha, it would be right here at the energy of the two 1s orbitals. And then this total binding energy would multiply by the number of electrons. If we wanted to rip both of the electrons out from H2, we would multiply that by 2. Now, the evaluation of alpha, for example, so just we could actually determine alpha because that's a hydrogen atom and we can solve that problem. But evaluating E plus is not a trivial thing to do, and typically that's something we do computationally. So this is just hydrogen, and I'm going to stop this video at hydrogen. We're going to continue on with other diatomics, but this kind of builds the structure. This is what we're going to use to build the LCAO-MO sets of orbitals, the diagrams, the electronic configurations, understanding bonding, whether it's magnetic, all of those things rise out of the MO diagrams. So until next time.